Salut Christophe.
Salut David, tu m'entends?
Oui,
Bon
tu vas
bah,
bien?
ouais, ça
Ouais,
va. Et toi?
ouais.
Bon.
Et-
Il- Ah, il y a déjà trois participants.
Oui, Antoine est là juste pour tester le micro et la
D'accord.
caméra.
Bonjour.
Ouais.
Ok. Du coup, bonjour. On va attendre Irène et puis je vais créer la salle alors.
Et je ne sais pas si après une autre personne joindre, si tu peux l'ajouter à la salle ou sinon il faut attendre tous les membres du jury pour créer la salle. Ouais.
Ouais, d'accord. En fait, ouais. J'essaie de savoir comment on crée la salle. J'ai oublié. Je vois plus
Ah, peut-être t'es
J'ai
pas.
pas les accès. Ouais.
Oui, c'est vrai. OK. Donc, je crois que maintenant,
Il y a Fanny qui dit qu'on nous voit bien sur YouTube.
euh,
Donc visiblement, il nous voit déjà. Ah oui, j'ai accès là.
OK, cool.
Ouais, c'est mieux. Ah, on peut créer plusieurs breakout homes.
Hmm.
En fait, je pensais qu'on allait voir tout le monde dans Zoom, mais c'est pas le cas.
Ah,
Parce
non.
que Fanny, elle nous voit à travers YouTube
Oui, c'est
et
vrai.
elle est pas vraiment connectée
Non,
sur l'interface de Zoom.
non, c'est vrai. Je pensais que c'était plus simple que de créer trois briques à tout, mais beaucoup de permissions et tout ça.
Ouais. Donc en fait, la break at home, c'est juste pour t'exclure toi.
Ouais.
En fait, dis-moi.
Oui,
Ok.
c'est vrai.
Bon, on attend les autres.
OK, cool. Très bien.
Bonjour Christophe.
Bonjour Yann, je t'entends bien, ça va?
Ok, tout va bien.
Ouais, on était en train avec David d'attendre que tout le jury se connecte pour que je puisse vous créer la salle et vous connecter.
Hello
Alors,
David.
Hello.
Voilà.
Vas-y, continue Christophe.
Oui, ce que je savais pas, c'est que en fait, j'allais voir personne sur Zoom. Je vois que vous et le jury et pas l'ensemble de l'auditoire.
La salle, tu veux dire le lien public?
Oui, le lien public. Enfin non, je veux dire les personnes qui sont liées au lien public, je ne les vois pas. Donc je peux pas, ils n'ont pas accès en fait, ils peuvent pas parler, ils peuvent rien faire à part
Non,
regarder.
ça c'est normal. Non, ils peuvent que
Ouais.
regarder.
Ouais, je pensais que j'aurais le droit de couper les micros. Ouais.
Ben non, mais on n'entendra pas leur micro.
Oui, bah, tout à fait, ouais, c'est ça. Bon, bah, c'est bien fait.
Bonjour Antoine.
Il n'est pas là, il revient.
Il s'est juste connecté. Ok.
Oui, pour
Je
tester.
suis là, je suis là. Je fais autre chose en parallèle.
Pas de problème.
Bonjour.
Ronald vient d'arriver.
Hello Ronald.
Hello.
Morning.
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 Good morning.
Nice to see you.
Nice to see you. Thank you
Good to see you too.
for joining early.
Well, actually, well, I already went on bike to my work at 7:15, so I'm awake. Don't worry. Well, luckily, we can work in the hospital again. So I have been vaccinated also, so it's going in the good direction. Also in the Netherlands, numbers are going down very rapidly now. So
Yeah, same in France actually.
things are becoming more relaxed, and so I can go to the office and then have a shower and then work. And you are still at home, I see.
Yeah, I'm at home, but similar to the Netherlands, the number of cases is decreasing fast at the moment. And
Yeah.
we can go to the office. So it's not completely back to normal yet, but we are in the right. I think it should improve soon.
Yeah.
We
So
cannot meet. We cannot meet at more than 6 at the moment. Before it was 3, so it's getting better.
That is still the same at home, because there you don't put up these plastic walls and those kinds of things. So at home we can now have 4 people, or if it's more people, they should come from the same family. Then that's also allowed. Because then, yeah. But otherwise, if you have, say, preventive measures like shields or so, you can meet with more, and you can guarantee this 1.5 meter distance. But yeah, of course, private at home, you don't make those.
No, I don't have any shielding at home. And I don't wear any mask at home.
No.
So Ronald, did you have time to just go through the instructions? Is that clear for you?
That's clear. Yeah. So
Okay.
I have them in front of me as well. So.
Okay. So as soon as Julia and Johan connect, we will go to the breakout room, because at the moment, I guess we are, I don't know whether it's broadcasted on the Zoom link. It is.
Yeah, we're live.
Okay. So all the
Yes.
small talk is there as well.
Yeah.
Hello, Johan.
Hello, morning.
Good morning. So we will wait for Julia. We will go to the other room so we can have a private chat, and then we will go back to the public room. So David, were you able to check that the public channel is working correctly?
Yes, yeah, it is. And I think Fanny's was already, she's checked it and it's working. So
Okay.
It's all good. I think there's a delay of about 20 seconds, but
that's fine. So how are things going, Johan, in Belgium?
Yeah, with vaccination, you mean, or?
Yeah, and whether you now have less, less constraint to go to work and to go out.
In principle, you can go out, but we don't. Yeah, last Friday I got my first shot, so in a few weeks I will feel better. Yeah, and we're still working from home all the time, so we're still encouraged to do that. And yeah, because we're all doing software, we can easily work from home. So.
Yeah.
Yeah, so now I'm at the office, but there is no one else here.
You have a private office, right?
Yes, yeah.
That also makes a difference. Yeah.
Yeah.
So which one did you get? Or don't you want to tell?
Moderna.
Oh yeah, Moderna, yeah.
Which is good. It's an mRNA. So
yeah.
I'm happy with that one.
Okay,
there was
Julia
no
is
choice.
here.
Yeah. Sorry?
Julia is here.
Hey, good morning.
Hello.
Morning.
Good morning.
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 So I guess we are all here. So Christophe, can you put us in the breakout room? At the moment, we are live on the public Zoom link. Is that a real background, Julia, or a fake one?
Now the background is real, but I'm not there. But I'm in London right now, so it's at least half fake only.
OK.
Ok.
Et il faut juste regarder sur le YouTube, voir le breakout room, parce que j'espère pas, mais...
Ouais, alors attends, je vais chercher le lien. J'ai pas encore eu le temps de me connecter sur le lien.
Je peux le
YouTube.
voir sur notre laptop.
Ouais, tu vois toi.
C'est bon.
C'est vrai. Le lien public, il avait été envoyé sous mail ou sous Discord ou...
Sur mail,
Sur...
Frédéric nous a envoyé un lien.
Ah oui. Ça y est, je l'ai. Je tente l'ouverture. Juste pour voir, je pense que c'est indépendant, je peux voir les deux à la fois. Alors oui, je suis connecté. En fait, c'est intéressant. Il y a un délai.
Oui, je pense 20 secondes peut-être.
Oui, facilement, ouais. Il voit ça en retard.
Ouais.
Okay,
Okay.
everyone is here. So maybe, Ronald, you can wait for two minutes because it's, or yeah, let's wait for another 2 minutes before you start. David, everything all right on your side?
Yeah, I think so. Well,
Good.
yeah.
So I guess you have tested the screen share.
Yeah.
But don't do it right now because
it works. It's fine.
Okay. During the introduction of the committee members, it's better that we stay on screen. And then you can share your screen.
We've got 17 viewers.
So you can see who is on Zoom.
I can't see who's on YouTube. I can see how many people are on YouTube.
Yeah, on YouTube. Yeah. Okay. So Ronald, you can start any time. And thanks again for accepting to chair.
Yeah, you're welcome. And yeah, herewith I would like to open the session, and I would like to welcome everybody to the public PhD defense of David Wallis to get a grade of PhD from the University Paris Saclay. The defense is unfortunately fully remote with live broadcast, and as indicated, I'm more than pleased to chair this committee. Before we start, let me introduce the other committee members. First, Professor Julia Schnabel, and she's professor for computational imaging and artificial intelligence in medicine at the Technical University of Munich in Germany. So thanks for joining. The second committee member is Johan Nuits. Professor Nuits is professor of the Faculty of Medicine at the Catholic University in Leuven from Belgium. Also welcome. We have Dr. Antoine Krikis. He's a senior research at the CEA and head of the Neurospin analysis platform in Saclay. And he's the representative for the University of Paris-Saclay. Then I'd like to introduce, as you know, Irene Buffat. She's director at the research of the CNRS. And she's the supervisor of David Wallis and the thesis supervisors. And finally, I'm chairing the session. My name is Ronald Boulaert, and I'm from the University Medical Center of Amsterdam from the Netherlands. Yeah, herewith I would like to give the floor to David for a presentation of about 45 minutes. And David, the floor is yours.
Okay. So, can you see?
Yeah,
can you see that fine? Can you hear me well?
Yeah, it's perfect, David. You can go ahead.
Okay, cracking. So, just to give an overview of the structure of the presentation, I'll start with a very brief introduction to the subject. I, of course, don't have time to go through the whole thesis, so I've picked out 4 pieces of work that I think are the most interesting and original, and then I'll wrap things up with a conclusion. So first, an overview of AI in medical imaging. So as of 2010, 5 billion medical image studies have been conducted worldwide, and the last 20 years have seen an explosion in the use of AI for medical image analysis. AI can make analysis quicker, more consistent, and more accurate. It's already used in many clinical situations and is predicted to fundamentally change the way clinical medicine operates in the coming years. So the graph here just shows the number of papers on PubMed with the keywords machine learning and medical imaging and how they've increased in the last 20 years. So in my thesis, I mainly focused on 2 methods of analysis, using handcrafted radiomic features and using convolutional neural network-based methods. So the diagram shows how for CNN methods, the image is input directly into the CNN, which then outputs as prediction. So I've put positive or negative here, but there could also be more than 2 classes. For radiomic features, we first extract defined mathematical features, then input these into a machine learning algorithm, and then this algorithm can output a prediction. And the key difference between the two is that radiomic features are fixed mathematical functions, meaning they don't change from model to model. For CNNs, the features change as it's trained, and this means it's often not possible to represent them as a simple formula or link them with a biological feature in the data. So this diagram details the process of using a machine learning model based on handcrafted radiomic features. So the data is first pre-processed, and usually images are resampled so they have uniform pixel or voxel resolution. Outliers are often removed, and the segmented region of interest is selected. The segmentation may have been performed by an expert or by a segmentation algorithm. The data is then discretized. So this is an important step, as the choice of bin size and type can affect the usefulness and robustness of radiomic features. Features are then extracted. So several feature types can be extracted. First order features are based on the histogram of pixel values, and these can include features such as the interquartile range or the skewness of the data. Shape features represent the actual shape of the ROI. So for example, its eccentricity or surface area to perimeter ratio. Texture features are higher order features and quantify relationships between neighboring pixels. And finally, filter-based features extract features after applying a filter to the image. So here we have as an example a wavelet filter. So in my thesis, I extracted features using pyradiomics. And then the next step is feature reduction. So often there are too many features relative to the size of the data set, especially in the medical imaging domain. And this could lead to overfitting when training a model. So features can be reduced by removing any that aren't correlated with the target variable, or by removing features which are highly correlated with each other. Finally, the features can be input into a machine learning model and a prediction can be obtained. So this model could be a linear regression model, a support vector machine, random forest, whatever. For CNNs, images are again pre-processed. Values are often scaled to be between 0 and 1, or to give the data set 0 mean and unit variance. And the images are then directly input into the CNN, which trains through learning the features discriminative for the task. It then outputs a prediction. And the example here is just a typical CNN architecture with a succession of convolutional and pooling layers, followed by dense layers and classification. So what was the motivation behind the PhD? The initial motivation was to use my knowledge of machine learning to build models that could be clinically useful in the analysis of medical images. And then following on from this, I became interested in comparing radiomic and CNN approaches and investigating how they could complement each other. Having spent some time building models and reading the literature, I also tried to answer the questions I thought were most pressing in the domain, looking at model interpretability and domain shift. So my first aim was to use machine learning to build a model to automatically detect pathological lymph nodes from whole body FDG PET-CT scans. So a bit of background on the problem. Mediastinal nodes are lymph nodes in the mediastinum, which is the blue region here, in between the lungs. And lung cancer can metastasize to these nodes, and this is prognostically important, severely affecting survival rates for patients. Currently, the nodes are identified by a physician, but this is associated with significant errors. A meta-analysis study found the sensitivity and specificity to be 0.59 and 0.93 respectively. So here are just some examples indicated by the green arrows. So pathological nodes are characterized by high uptake on the PET in the presence of a lymph node in the mediastinal region. So hence hybrid imaging is needed, but they can often be confused with other sources of inflammation. So the aim of the project was to build a model to take as input whole body PET-CT scans and output images with suspicious nodes automatically labeled. And this would save physicians time and increase consistency of nodal categorization. So to do this, we had a cohort of 134 patients labeled by an experienced physician, giving 172 positive nodes in total. And we reserved 29 patients for testing, only using them at the very end of the project. And the hyperparameters in the model were optimized using a validation set. As mentioned, there's a large error in labeling by experts. While some of the nodes can be biopsied, a lot can't be because of their positions. meaning a true gold standard isn't possible. So to measure the success of our model, we instead compared the variation between our model's predictions and the physician's labels to the variation between the predictions of 2 physicians. And we therefore had the test set labeled by a second physician and compared their labels to the first physician's. So I'll briefly go through how the model works. So first, the images were pre-processed. The PET and CT images were resampled, rescaled, combined, and automatically cropped to leave only slices in the lung region. This rescaling was done globally with respect to the whole data set, so that absolute differences in PET and CT values were maintained. Because the nodes were so small compared to the sizes of the scans, I had to use a 2-stage process to detect them. So the images were first fed slice by slice into a U-net, which output suspicious regions. And this was a sort of rough sorting stage. So the aim was to have a high sensitivity, so I didn't want to miss any nodes. And these regions were then divided into 64mm cubes, and these were predicted as positive or negative using a ResNet network. This gave predictions at each coordinate on the images, which were compared to the physician's labels. So the bars show the performance of our model versus the physician and the performance of the first versus the second physician. And the sensitivity and specificity of our model versus physician 1 was 0.87, 0.94. And this is an improvement on the best published results from Wang et al., who achieved a sensitivity and specificity of 0.84 and 0.88. Because there was no ground truth, it was impossible to know whether our labels were true positives or mistakes by the physician. So comparing our results with those of the second physician, we see that the variation between our model and physician 1 was less than the variation between the 2 physicians. So importantly, this is also the first model we know of that goes directly from whole body scans to node detection. So all previous published works required the lymph nodes to be pre-labeled. So here are just a couple of examples visualizing the output of the model. So the white crosses are the nodes marked by the physician, and then the green areas are nodes predicted as suspicious by the model. And this output could be used clinically to aid in diagnosis, and you can see it could guide physicians towards regions of interest. So we then acquired data from a second, newer scanner, and again had the mediastinal nodes labeled. So this new data set comprised 59 patients with 69 positive nodes. And the aim was to investigate the problem of domain shift. So often machine learning models trained on data from one scanner perform poorly on data from a second scanner. And this of course limits their utility. So I plan to test the model on this new data set with and without transfer learning. I therefore split the data set into 30 patients for transfer learning training and 29 for testing. And this is just the details of the data set here. And the figure shows the images from the 2 scanners. So you can see that the new scanner, scanner 2, gives much better images compared to scanner 1. So this bar chart compares the performance of the model on data from the first scanner to data from the second scanner with and without transfer learning. So to implement transfer learning, I trained the second phase of the model for a further 20 epochs with a smaller learning rate of 10 to the minus 8. And you can see that without transfer learning, the model performed very poorly. That's the yellow bar here, with the sensitivity of only 0.53. However, after adapting the model using transfer learning, the sensitivity increased to 0.8, comparable to the data from the first scanner. So as is clear from my manuscript, I spent a lot of time testing various approaches and parameters for this task. And this was my first project using machine learning models. So it was also a chance to learn how different factors affected the results and what worked and what didn't. I tested using MIP-based images, immediately splitting whole images into cubes and using self-supervised transfer learning. And more recently, so this isn't in the manuscript, I tried using only phase 1, treating the task as a segmentation problem. However, I found that this left far too many false positives. With more careful thought and optimization, I'm sure some of these methods could produce excellent results, but there are of course infinite experimental possibilities, so I satisfied myself with this setup. I also spent a lot of time optimizing hyperparameters for the model, and I found that changing these parameters can dramatically affect the performance of the model, and even retraining a CNN with the same parameters can sometimes give very different results. So ideally, we don't want retrained models to give different results, and this was investigated in later chapters. Finally, when applying the model directly to data from a different scanner, the results were very poor. and this highlights one of the challenges of widely adopting deep learning models. However, with transfer learning, the model was successfully fine-tuned to the new data. So just to conclude, I successfully built a model that can go from whole body FDG PET-CT scans to pathological lymph node localization. This model was tested on data from the same scanner and, with the use of transfer learning, successfully adapted to data from a different scanner. And this work has been submitted to the European Journal of Nuclear Medicine and Molecular Imaging. So having used radiomic features when working on the previous problem, I became interested in comparing the merits of radiomic and deep features. In the manuscript, there's quite a lot of work comparing the performance and interpretability of the two approaches. So one of the disadvantages of using radiomic features is that the tumor or region of interest needs to be segmented. But this is a time-consuming task which can have considerable intra-observer and even intra-observer disagreement. So I thought that radiomic features could be powerful enough to extract useful information without a precise segmentation, instead just using a regular cubic region of interest. So in this part, I investigate this hypothesis. So I ran tests on two data sets. First, an FDG PET breast cancer data set consisting of 289 patients, with each labeled as triple negative or non-triple negative. And tumors have been segmented using a 40% SUV max threshold, supervised by a reader. The data were acquired from two different scanners, one a Gemini GX from Philips, and the other a Discovery 710 Elite from GE. And this table just shows the distribution of data within the scanners. And the figure shows an example image with the tumor clearly showing up as a high SUV region, indicated by the green arrow. Secondly, I used the publicly available lung nodule analysis, or LUNA dataset. And this consists of lung CT scans of 888 patients with pathological candidate nodes labeled by an algorithm. So in total, there are 750,000 or so candidates. And of these, 4 experienced radiologists have labeled 1,166 as actual pathological nodes. And so the task is to classify the candidate nodes as positive or negative. And there are obviously a huge amount of negative nodes. So to speed up training, I randomly selected 1,166 of these. Now, there aren't any explicit segmentations available for this dataset, but I thought that if a radiomic model could achieve good results, this would indicate that precise segmentation isn't necessary. So here are just some examples of positive and negative nodes, and you can see that they come in a variety of shapes and sizes. So the first step was to extract radiomic features from the images. For the breast data set, the voxels were resampled to 2 by 2 by 2 millimeters cubed, clipped at 40 SUV, and discretized with a bin width of 0.3125. The tumors varied quite a lot in size, as shown in histogram on the right. So the maximum 3D diameter of the tumors ranged from around 15 millimeters to over 140 millimeters. So I extracted radiomic features from ROIs using the precise segmentation and from cubic ROIs of different sizes. And the diagram below shows examples of the different ROIs in green. So here we have the precise segmentation, then cubic ROIs of different sizes. First order, texture, and filter-based features were extracted. And for the precise segmentations, I also extracted shape-based features. So this gave a total of 341 features per image for the cubic ROIs and 355 for the precise segmentations. And because the data were from 2 scanners, I used Combat to harmonize the data, using the TNBC status as a covariate. So for the LUNA dataset, the voxels were first resampled to 1 millimeter and clipped between -1,000 and 1,000 Hounsfield units, and discretized with a bin width of 25 Hounsfield units. I extracted radiomic features from cubic ROIs of side length 8, 12, 16, and 24 millimeters. And I extracted the same features as for the breast dataset, giving 341 features per image. And the figure shows some 24 by 24 millimeter squared slices, which indicate the sizes of some of the nodes. So you can see that some are large, kind of around 24 millimeters in diameter, whereas some are only a few millimeters across. So as mentioned, there weren't any segmentations available for this dataset. So instead, I compared the performance using radiomic features to that using a CNN. And the idea was that if the performance of a model built using radiomic features could come close to that of a CNN, this would suggest that a precise segmentation isn't necessary. So I used the same CNN setup and architecture as the second place solution on the LUNA leaderboard. I didn't use the best place solution as the method wasn't very clear. So just to go on to the method used, these features that I'd extracted were then used to build machine learning models. So after feature extraction, they were rescaled to have zero mean and unit variance, using the training data to calibrate the rescaling. Given the size of the data set, there were far too many features, and the model would probably overfit. So I therefore reduced the number of features by using univariate analysis to find the 100 that best distinguished two classes, then removed any that were highly correlated with each other. So for two correlated features, the mean absolute correlation of each feature with respect to all other features was calculated, and the feature with the largest mean absolute correlation was removed. The features were then used to train an SVMs. So the AUC and associated error were calculated using a 100-fold cross-validation, and the setup was the same for both datasets. So the bar chart shows the performance of the models built with different ROIs for the breast dataset, and note just that the axis actually starts at 0.5. So you can see the AUCs are quite similar for different ROI sizes, and notably the performance when using 14mm ROIs is actually significantly better than when using precise segmentations. And this is despite many of the tumors being considerably bigger than 14mm in diameter. At much larger cube sizes, the performance starts to drop off a bit. And here we have the results for the lunar dataset. And again, note that the y-axis starts at 0.5. So we can see that the performance is fairly robust to changes in ROI size, but starts to drop off at cube sizes of around 24mm. The best performing radiomic model was with 12mm cubes with an AUC of 0.93. So for comparison, the CNN achieved an AUC of 0.97. So although the CNN outperforms the radiomic models, the radiomic models' performances are still quite high. And this again suggests that precise segmentation isn't necessary for radiomic features to extract information relevant for classification. And the CNN was trained with a relatively large amount of data, at least for a medical imaging data set of around 2,000 images. So we therefore probably expect the CNN to outperform the radiomic model anyway. So how do we explain these findings? So one explanation could be that radiomic features are robust to changes in ROI size, and they can therefore extract relevant information without a precise segmentation. So to test this, I used the SVM coefficients to find the most important radiomic features in the segmentation-based models. I then correlated these with the same features extracted from the cubic ROIs. And the lines on the graph just show how the different features correlate. You can see that of the top 4 features, 3 correlate very highly, especially an ROI size of 10 to 14mm here. So as seen on the bar chart, this corresponds to where the models actually perform best. As the ROIs get larger, the features correlate less strongly, and this matches with a drop in model performance. So for the green feature, which is the mean of a wavelet-based image, the correlation is just low for the whole thing. So clearly not all features correlate with and without the precise segmentation. So similarly for the lunar dataset, I correlated features extracted from 12mm ROIs to those extracted from other ROI sizes. And again, you can see that the correlation is quite high. The nodes are of varying sizes, but the radiomic features are powerful enough to extract useful information, even with a varying amount of background. So both datasets demonstrate a good performance without precise segmentation. Using cubic ROI still requires the tumor to be located. This is far, far easier than performing a full segmentation. So on this image here on the right, you can see it's easy to locate the tumor, which is just a high uptake black dot. So there's a slight bias in my findings for the breast dataset. So I used the center of mass of the segmentation as the center of the cubic ROIs. So did implicitly use the segmentation. However, I don't think that moving the center a few voxels would greatly affect the results. The tumors in both datasets are hyperdense regions surrounded by hypodense regions, which may explain why precise segmentation isn't required. Changing the ROI size just adds or removes background. So the importance of having a precise segmentation may depend on the exact task at hand, but by demonstrating a good performance on 2 very different datasets, I've shown that it's not always necessary. So to conclude, I showed that the time-consuming observer or algorithm-dependent process of segmentation may not be required to extract useful radiomic features for classification. So this could remove one of the key disadvantages of radiomic-based studies. And I've written a paper on this and plan to submit soon in the next week or so. So when comparing radiomic and CNN models, I used a publicly available brain MRI dataset. However, I began to suspect it contained a bias that had not been mentioned in other studies. So in this part, I discussed the resulting investigations. So first, an introduction to clever hands. The clever hands effect is the danger of unintentional cueing of the desired behavior by the questioner if the experiments are not carefully designed. So it's named after a horse called Clever Hands, who everyone thought could solve maths problems. However, it turned out he wasn't a mathematical super horse, but was just taking cues from observers. So I suspected a similar bias was at play in the public data set I've been using. And this is just a picture of Clever Hands in action in the early 1900s, I think it was. So the data set in question consisted of 3,064 2D T1 weighted MRI brain images from 233 patients. And there were 3 types of tumor: meningiomas, gliomas, and pituitary tumors. And the tumors have been delineated and classified by 3 experienced radiologists. The images were 512 by 512 pixels with a pixel size of 0.49 by 0.49 millimeters squared. And they were a mixture of axial, coronal, and sagittal slices. So here are some examples on the right, just showing with the tumor segmentations in red for each. And here's just the summary of the data set. So why was I suspicious? Well, lots of the published studies use CNNs to classify the images with whole slice inputs, not using the segmentations. Of course, the original scans must have been 3D, but the data set consisted of only 2D images. So these 2D slices must therefore have been pre-selected. And the different tumor types grow in different areas of the brain, so this pre-selection could maybe be used to cheat. For example, pituitary tumors grow in the pituitary gland, which is in the center of the brain. So looking at this image on the right, if a slice were chosen at position 2, it would therefore be easy to rule out a pituitary tumor, whereas slice 1, it'd be quite likely it was a pituitary tumor. So this table lists some of the previous studies that used the dataset. I'm not going to go through them all, but the original study was published in 2015, and it's since been cited by 177 articles according to Google Scholar. And looking through these articles, I haven't looked through them all, but on a lot of them, many of them use whole slice inputs and don't reference a potential bias. So to test my theory, I ran several experiments. And in each case, images were pre-processed by cropping them to 450 by 450 pixels and rescaling to between 0 and 1,000 using the 99th percentile. And I then extracted features in each of the 6 experiments and used these features to train SVMs. So the SVMs were trained similarly to in the previous work, with a linear kernel and a C-value of 1. And the features were first reduced using the same feature reduction method as in the previous section, and cross-validation was used to give a performance and associated error. So I'll now just talk through the 6 experiments that I performed. And the idea is that each one alters the images in some way to test which parts are being used for classification. And this then allows us to determine if there are non-tumor-based biases in the images. So for the first experiment, I extracted radiomic features from the full 450 by 450 pixel slices without any tumor segmentation. So that's this whole slice here. And then in experiment 2, I used the segmented tumor region only, as in conventional radiomic studies. Experiment 3 extracted features from the full tumor slices, but with an 80 by 80 pixel zero intensity square covering the tumor. So you can see the square just covering the tumor there. Experiment 4 thresholded the images by setting all pixels less than 100 to 0 and all above to 1. And this left images with just 2 intensity levels, effectively just an outline of the skull. So that's just this here. In experiment 5, only 3 features were used, designed to capture the orientation and position of the slice without having any tumor-based information. So these were the number of 0 intensity pixels, which measures the size of the background region, the maximum intensity in the image, and the orientation of the slice. Finally, experiment 6 combined the features from experiments 1 and 2. So here are the results. And we see that experiment 1, using the full tumor slice, gave a high accuracy. It's very similar, or actually slightly better, than using the segmented tumor region in experiment 2. So given these 2 results, we could conclude that the radiomic features used in experiment 1 were capable of extracting useful information regarding the tumor, even with this whole slice view. However, I thought this unlikely. So the tumors are very small compared to the slices, and there's a lot of extratumoral heterogeneity, which would surely obscure tumor-based variations. So then experiment 3 achieved a similar accuracy, occluding the tumor, showing that textural information within the tumor wasn't necessary for classification. So we may still hypothesize that there was enough information in the surrounding tissue, or the occluding square itself was being used by the model to locate and classify the tumors. But then in experiment 4, I erased all textual information, leaving just the skull outline. So you can see the accuracy dropped, but it's still much higher than random. And then for experiment 5, using the 3 features also gave very high accuracy, showing that we can classify the images using the positions and orientations of the slices alone. And then finally, in experiment 6, the combination of features from experiments 1 and 2, we see that the accuracy is much higher than the individual experiments. And this shows that these sets of features are bringing different information, which are useful. We're extracting different information from the images that can be used by the model. So to understand the high accuracy in experiment 1, I then tried to understand how the features were extracting information to position and orientate the slices. So I used the SVM coefficients to find the most important features, and I found that these were mostly wavelet based. So plotting histograms of the pixel values of these wavelet based images for each class separately, we can clearly see that there are in fact differences in the distributions. So here you've got the meningioma, the glioma, and the pituitary tumor. You can see that there are differences in these wavelet based pixel distributions. So then the question is, are these differences due to the tumors or due to the orientations and positions of the slices? So plotted here are some examples of the wavelet-based images. And you can see the original image here, which is on the left, with the tumor delineation in red. And then you've got the corresponding wavelet images here. So the tumor, you can see it's not highlighted at all in the wavelet images. So clearly they're not picking up the tumor. And instead, what we see is that the images highlight the border of the head here and here. And this makes sense if there's a selection bias. The wavelet-based images highlight the skull outline, and this is indicative of the position and orientation of the slice. So the result clearly demonstrates a bias in the data set, as tumors can be classified with no information regarding the tumors themselves. So as I've shown, many studies used the data set without addressing this issue, using CNNs trained on whole slice inputs. Now, we can't know whether the models in these studies truly used information within the tumor or used the positional and orientational information hard-coded into the images. And they may have used a combination of the two. So this finding demonstrates the importance of understanding the data. Many of the published studies didn't have MDs in their author list, and it could be that medical experts would have noticed this issue. And I've submitted an article on this subject to medical image analysis. So moving on to part 4, when I was investigating radiomic and deep features, I began to wonder whether the two methods could complement each other. So in this final section, I propose a method to interpret CNNs using radiomic features. So CNNs models often perform very well, but a common criticism is that they lack interpretability. So this is an especially pertinent problem in our field, because clinicians don't just want like a binary positive, negative answer. They often want an explanation as to why that's the answer. And this would also aid us in sort of deeper biological understanding of the processes. So of course, many methods have been proposed, but the resulting interpretations are often incomplete or unsatisfactory. And in this section, I propose distillation models as a new complementary interpretation method. So this is actually something I've worked on in the last couple of months. So I've added a bit more detail since sending you the manuscript. So first, I'll just summarize the work that you've already seen. So in the manuscript, to interpret deep features, I tried recreating them using radiomic features. So the graph on the right, which you may recognize or remember, something like this. So it shows an example with the distributions of the deep features in blue, and then the recreated radiomic-based features in red. So the distributions are separated by class. So for example, for deep feature 1, the negative class is the distribution here on the left, and the positive class is on the right, and equivalent for the radiomic-based features in red. And you can see that in general, the radiomic-based features mimic the deep features fairly accurately here. And then I also looked at how replacing the deep features with radiometric features affected the performance, effectively seeing if you could replace a deep model with a radiometric model and get a similar performance, and it may be more interpretable. So I found that this success of the replacement depended on the data set. So then in the last couple of months, I've added to this a bit by showing how the approach can be used practically. And in this section, I'll just kind of go through these new findings. So this diagram illustrates the experimental setup. So there's the input data here, the input labels and the input images are used to train a CNN here, which outputs some predictions. And the radiometric features are also extracted from the images, and these are used to train a distillation model. And the type of algorithm used for the distillation model should be easily interpretable, basically. So in the manuscript, I used a random forest, but recently found that a gradient boosted tree-based model gave a better performance. So the key point is that the labels used to train the distillation model are the predictions of the CNN, i.e. they're the values ranging from 0 to 1, not the ground truth labels. So this trains the distillation model to mimic the CNN, even if the CNN's predictions are incorrect. And this distillation model can then be interpreted, with the interpretations revealing how the CNN's predictions correspond to radiometric features. So to test this method, I used the brain dataset described earlier, but with the segmentation to avoid the bias. So I extracted first order, shape, and texture-based features from the images, giving 116 in total. But I didn't use filter-based features, as these are often actually not very interpretable at all. And then these features were used to train a gradient boosted tree model, as I said, using the CNN output predictions as labels. And once trained, I used various interpretation methods to try and understand the model and therefore understand the CNN. So the first question to ask of the distillation model is, does it mimic the CNN's predictions with a reasonable accuracy? Because if it doesn't, it'll be useless for interpretation. So the AUC of the distillation model versus the CNN's predictions was 0.93, which is a pretty good agreement between the models. Secondly, does the distillation model achieve a similar performance against the ground truth compared to the CNN? So the AUC of the CNN versus the ground truth was 0.95 compared to 0.93 for the distillation model. And this is reassuring. So we probably expected a small drop off as the distillation model is simpler than the CNN, but this means that the distillation model should still be useful for interpretation. So as I'm sure you recall, there were 3 classes in this data set: meningiomas, gliomas, and pituitary tumors. So I first used permutation importance to see which features were most important in classifying the images. And the 3 graphs here correspond to the 3 classes. And just focusing on the graph on the left, we can see that the skewness, total energy, and median values of the tumors highly affected their classification as meningiomas. So, and from this, we can infer that the CNN is picking up on these features for its classification. So looking into more detail at these 3 features, we can view partial dependency plots. So these show how the value of each feature affects the distillation model's predictions. So here, the graph on the left shows that a skewness below 0 means the model is more likely to predict the image as meningioma. And then it drops, and then above 0, the skewness actually makes it less likely. So we can see that a negative skewness is indicative of meningioma, at least according to the distillation model. And similarly, we can see that a high total energy and high median value of the tumor are being used by the CNN to predict tumors as meningiomas. So we can also go a step further than this by looking at how the features interact. So the graph on the left shows the interaction between the tumor median and skewness in predicting meningiomas. So the red areas indicate a positive impact on the classification, and blue areas a negative impact. And it shows that it's a high median combined with a low skewness that leads to a meningioma prediction. And similarly on the right, we can see that a high median combined with a high total energy leads to a tumor being classified as meningioma. And then we can also use the SHAP values to explain individual predictions, for example, to try and explain an incorrect prediction. So here's just an example tumor that was classified by experts as a glioma, However, the CNN predicted it as a meningioma. And the gradient boosted tree also predicted it as a meningioma with a similar degree of certainty. So looking at the SHAT values, we can explain and understand why. The total energy and skewness of this tumor both led to the false prediction. So clearly in this tumor, these features are uncharacteristic, at least according to the CNN. This is leading to a false result. So these results demonstrate a new method to interpret CNNs using radiomic features. Now, I wouldn't say it replaces other methods. I think each method has its advantages and disadvantages, but it could complement existing methods. So other non-radiomic features could also be used to build the distillation model, depending on what is most clinically useful. So there are a few caveats. So one, it depends on the radiomic features themselves being interpretable. So sometimes higher order texture features are quite opaque, and filter-based features are often very hard to interpret, actually. And then we also need to check that the distillation model is sufficiently powerful to mimic the CNN. So as I described, you need the distillation model to be able to mimic the CNN, or your interpretations of the distillation model won't match those of the CNN. I've also tested this on the LUNA dataset, but don't have time to show the results here, but they were again quite promising. So finally, I'll just conclude with a summary of my main contributions during the thesis and my perspectives for the future of the field. So over the 3 years, I explored different clinical and methodological problems, focusing on the areas I thought were most interesting and challenging. So there are many more things I'd like to have investigated further. I probably have more questions now than when I started my PhD. Looking to the future, I think a key issue is the lack of clinical adoption of AI models. So there are so many incredible studies published, but rarely do these find their way into real-world practice. And one problem affecting the whole of AI research that I would like to investigate further is the lack of understanding in deep learning theory. So why do networks generalize so well, despite their enormous capacity to overfit? How do batch normalization, dropout, and transfer learning work? Answering these questions would help us better understand the models we're using. And this leads into my second point about a lack of interpretability. So in many cases, models won't be used clinically if their predictions can't be explained, but not enough efforts made in the literature to address this. So perhaps we need to take a step back from producing ever more complicated models, solely focusing on accuracy or AUC, and try to build simpler models that combine good performance with interpretability. So more close collaboration and consultation with medical experts could help align the clinical goals with the goals of the AI engineers. Finally, the lack of data. So this is probably the most important factor determining the success or failure of a machine learning model. While in other fields, networks are trained on millions of images, medical imaging datasets are typically of the order of hundreds of images. So most published studies use data from a single center, and as I demonstrated, without adapting the models, this means they'll often be useless on data from a different center. So some model adaptation and data sharing solutions have been proposed, such as the transfer learning method I showed. And I hope that in the future, more data sharing will allow for larger, more heterogeneous data sets. So despite these issues, I'm generally hugely optimistic about the field. I think so much progress has been made, even in the last 3 years I've been working on it. And I look forward to continuing to work and try and answer these questions in the future. So I've had such a good time over the last 3 years, and I'd like to thank all my friends and colleagues at the CEA, Institut Curie, Hybrid, and everywhere else for their help and support. And finally, just a massive thank you to Irene for being generally pretty awesome as a supervisor and always being there to help with good questions and her time, and me sending presentations at the last minute and things. So a big thanks to Irene. And that's it, done. So thanks very much, and I guess open to questions.
Thank you very much, David. Can you stop sharing the screen? So probably we get a visual back. Okay. Thank you very much for the presentation. It was a clear overview of what you have been working on. And indeed, we can move on with the defense and the questioning. I'm more than happy to to open this formal part by asking Professor Julia Schnabel to start asking you a couple of questions. And, the floor is yours, Julia.
Thank you very much. Thank you very much, David, for this really nice and comprehensive presentation, which I've enjoyed very much after reading your thesis, and it clarified a few questions I had. So it will be hard for me to ask additional questions now, but I will give my best. So you've really nicely structured your presentation into these 4 parts, starting off with the lymph node detection work. And I was wondering there, in your pipeline, there's always this pre-processing step, which is always a bit kind of glossed over in articles. And it always consists of something, we rescale the images, we sample them to uniform pixel size or voxel size in 3D. And I was wondering how much thought have you spent on that, whether this is a good thing to do in medical imaging where we deal with anisotropic voxels, and also where we deal with quantitative intensities which might be affected by this.
Interesting, yeah, because one thing I tested in the mediastinal chapter was looking at different voxel sizes, because obviously using hybrid imaging, PET CT, you've got the PET images which were 4 by 4 by 4 millimeters cubed, and the CT which were more like 1 millimeter cubed. So obviously, while you don't want to lose information, if you go, if you have 1 millimeter cubed voxels, it means you're having huge interpolation in the PET. So I think I tested with 1 millimeter, 1.5, and 2 millimeter cubed voxels. I didn't find it made a huge difference, but I think the 1 millimeter cubed voxels were slightly better. So in this case, yeah, I used that. I think it depends. So I think I've seen CNN studies that use not necessarily isotropic voxels. So they use voxels that are, for instance, if you've got the interslice difference is often bigger than the sort of intraslice. So I think I've seen CNNs using like smaller voxels in plane, and that seems to also work. So I don't think you necessarily have to make the voxels isotropic for a CNN to work. I think with having done all the tests, it's like I discussed in the presentation a bit, having done all the tests, you realize that there's kind of no hard rules, it almost seems. And then even like looking in the literature, there's no hard rules, which is kind of very frustrating. As I said at the end, I think the lack of kind of understanding is frustrating. And I don't know whether that's a fundamental thing. Like, do you just have to test problem by problem each time? There's no kind of rule or thing theory that you can decide, or do we just not understand it deeply enough? Because I agree, it's strange that I'm sure most published studies effectively do this kind of testing of pre-processing parameters, but it's not really kind of discussed or studied. And yeah, I agree. But yeah, for mine, I did it kind of experimentally, and I did test a few, and I just found the one that worked best. But as someone from a theoretical background, it is not entirely satisfactory, I would say.
No, I mean, as they say in England, the recipe is in the pudding, so it depends the outcome is in the end.
Exactly.
Justifies the means. I was also quite intrigued by your domain shift, which is a huge problem, right? You train on one fairly small data set in one hospital, and then want to apply it to another data set acquired in another hospital or across multiple hospitals or a different scanning system even, and how do you deal with that? And you dealt with it by transfer learning, by freezing some and wiping some neural network layers and retraining and testing. I was wondering whether you've looked also at things like adjusting some parameters or some pre-processing, in fact, going back to the pre-processing, to deal with maybe different point spread functions between the different scanning systems. Have you looked into that a bit?
No, I didn't actually. So the one thing I did, I resampled so they had the same voxels and the same distributions in general. But yeah, I didn't look at that. So it was I think the final chapter in the thesis, which I think it's a really interesting topic. But unfortunately, I found I didn't have enough data to really make the results that significantly different. I don't know if you noticed on the graphs, because my idea was I wanted to try and compare different methods of domain adaptation. And then I also wanted to see how the number of data you had available for domain adaptation changed the kind of accuracy or performance. So yeah, I think it's important, but not only did I not have enough data for that to be significantly significant, it would also be very interesting to see how different scanners, so if a scanner's more different, do you then need more data for domain adaptation?
Yeah.
How does that affect different methods? Yeah, because yeah, surely a scanner that's more different is going to be harder to adapt to your model.
So my latest take about domain adaptation, which might be very controversial, is that you more require more data augmentation, and then you don't need domain adaptation. I mean, you need more data and full stop, but I mean, in lack of that, augmentation can go a very long way, actually, and maybe doing it a bit more clever way than people are normally doing it these days. So one thing you could have tested, I was wondering whether you did, and probably done, because usually only very small bit goes into a thesis at the end of 3 years, right? Is because you've got data from one scanner, data from another scanner. So you tested, trained on one, tested on the other with and without domain adaptation. Did you try to mix, split each data set in two and train on one mixed data set and test on the other mixed data set? And what were the outcomes if you did that?
Yes. So I think in the last chapter I trained on a mixture and then tested on scanner 2. And actually I found, I guess this is kind of similar to what you were saying about augmentation, because in a way, when you augment your data with kind of intelligent augmentations, what you're trying to do is mimic data from several different scanners, right? And I found that using a mixed data set from the 2 scanners actually worked very well. And yeah, I did also test that model on data from the first scanner, and I found that it performed similarly to a model just trained on data from scanner 1. So I found that training on a mixed data set was very good, at least as much as I could deduce, because I didn't have much data, as I said.
Great, thank you. One small thing on that first part of your presentation today was on hyperparameters, where you said the choices always has to be made and you have to test and find the best hyperparameters. Did you look into training learning some of the hyperparameters at all?
No, I didn't, to be honest. Again, it was very empirical. So I guess kind of it's sort of educated guesswork is what I would call it, I suppose. Yeah.
Great.
But yeah, so you mean almost having a dynamic training which adapts depending on, yeah.
Okay, so maybe on part 2, I just have a few questions. I really like that you went back to the good old days for me, to the radiomics features, and also asked yourself how good is good enough? Do you need a precise segmentation for radiomic feature extraction? Did you find at all for the lunar data set? I'm working with that quite a lot as well, or not I, but my PhD student. Is there some correlation between the size of the nodule versus the box size which you use to classify it? I assume you did classification into benign and malignant, or what was it? Yeah. So because there is this correlation that small nodules are more labeled as benign and big nodules are more labeled as malignant, which we don't quite know whether this is true in cancer, because they could have small aggressive nodules just because by virtue of being small, they might be labeled as benign, which they aren't. But if you've got a very big box and a very tiny nodule inside, you basically almost average out a lot of the radiomic features which the nodule might reveal and look at more at the background. So indirectly, you might be classifying size. Have you done a plot of size versus accuracy in any way?
No, I haven't actually, but yeah, like I showed on the graph. So what I found that was in general, when the box got too big, effectively the accuracy reduced.
Yeah.
So clearly actually it only required a very small box around the nodule itself to classify. But yeah, it would be interesting to see if as you go larger, maybe it depends. But I may have to look at the sizes of the nodule and stuff. But there's definitely a relationship between the size of the nodule and the label as pathological or not. Because the bigger ones are definitely more likely to be pathological. That's very true.
Yeah, and then the big box might even be too small for your nodule in some cases.
Yeah, exactly. Although interestingly, with the breast data set, and this is different because it was PET, but I found that the box didn't have to cover the whole nodule. Again, that's why I say it's probably quite task dependent, because for PET, a lot of it probably lies on the kind of the maximum SUV uptake. So maybe you don't need a very big cube. Whereas if you're on different modalities, you might need kind of more complicated textural features, and therefore maybe you need a larger amount of the tumor within the box effectively.
Great. So I've got one final question, if I may, and that is kind of you discarded segmentation in a way. You say you want to go straight to the data, straight to the whole body images, and don't want to kind of segment things out first, and ideally. But there are lots of good networks out there which do now multi-organ segmentation, and there are lots of good networks out there which solve several tasks simultaneously, like segmentation and classification. And I was wondering what your view on that is, because I think it might have helped in some cases. If you look at, say the brain, you segment the brain plus the tumor and plus the classification task in one. It also gives you indirectly some spatial context, I guess, where the tumor is. It's more likely to be one type of tumor than the other, and these tasks can help each other. So I was wondering whether you had looked into those.
I hadn't looked into using one so much. I guess I don't want to say that segmentation is never useful, or don't use segmentation. It's just in some situations where, for instance, with the breast data set, you're segmenting just the tumor, and effectively you've got a process which takes some time there, and you're just using it for classification. In that sense, my point is, like, question whether it's actually needed, question whether there's added value in using that segmentation before immediately thinking I have to segment in a way. Of course, as kind of deep learning based segmentation algorithms get better, in a way it can become more automated. So in a way, now it doesn't have to be all done manually. However, even then you've got the problem of different segmentation algorithms giving different results, and these actually they affect radiomic features quite a lot. So the precise algorithm you use to segment can mean that a lot of radiomic features aren't robust to segmentation. So
yeah, I would agree, actually, because segmentation is a bit of an auxiliary task which we do to focus on where we want to focus.
Yeah, I guess maybe for like dosimetry it's required, and radiation therapy, but yeah, maybe not for certain like classification tasks.
Yeah. But in the end, classification is probably based on some voxel analysis anyway, so you will focus at the right place. And your attention maps, the GradCam images showed that this is where the network is focusing, so it is probably indirectly segmenting. Yeah. Thank you very much. That's all the questions I had, and I'd like to congratulate you on your work.
Thanks very much.
Thank you very much, Julia. And now we can continue with Johan Nuits, Professor Nuits, and I will give the floor to Johan to continue the defense.
Yeah, thank you. And thank you too, David, for a very nice presentation. Yeah, and as I already said, I enjoyed reading your thesis a lot too. So congratulations on both parts. Although it's a bit early, we first have to do the deliberation, I suppose. Yeah, for the questions, I would like to continue where Julia left off with the classification versus segmentation. So I also made a note on that in my report. So, but I have to admit, you have more experience with deep learning than I have. So, but I'm very interested to know what you think about it. So my own feeling is a medical doctor who would learn to interpret these images doesn't learn to classify, but first would learn to segment. So the other medical doctor, the teacher, would say, look, you see these hotspots, that's where you have to look at. And if you see them like this and this, then you classify it as positive and otherwise as negative. To the network, you do it differently. That's at least how I understand what you did. You show the image to the network and you say, and now you should classify this as disease, but you don't say why. So the network has to look everywhere in the image and they're all different. So I could imagine it takes a lot of data for the network to just figure out should actually be looking at hotspots in the bed or at small blobs in an environment. So I would postulate that even if you have to do a classification, it's probably better to do some kind of segmentation in between, or maybe force the network to not only output the classification, but also a segmentation, just to make the training more informed and hopefully get away with less data. What do you think? Does this make sense to you or not?
Yeah. So I've seen some studies that where they've got a segmentation, you effectively do two tasks at once. So you can say segment whilst also classifying, and in a way I think that is good because you've almost got more data for the model to learn off, I guess, in a way. So for my specific example with the mediastinum, I guess if I had explicit segmentations of the mediastinal nodes, perhaps I could have used those. So in phase 1, as you saw, I instead just used kind of spheres for the segmentation. I think in your report you mentioned something about kind of maybe using a threshold on the PET to try and kind of make a segmentation. Yeah, but perhaps it'd be possible. It's quite kind of, the PET images are quite sort of messy, I guess, in a way, because it's not necessarily you have like the nodule PET and then lower in the background. You know, a lot of the time you have the PET kind of spread out across a long period. So, and it's not even necessarily a maximum on the PET where the node is. So there may be a way to do it, but I think, yeah, it would be quite difficult in this case. I think if I'd had segmentations available, I definitely would have used them in some way. I'd also say that in terms of, I did actually look at kind of introducing a prior. So introducing like a PET threshold in a way. So saying ignore any regions that are below 2 SUV, because that's quite a common threshold for mediastinal lymph nodes. But I found it didn't actually improve the accuracy because the UNet was already, it was already kind of doing that. It was already finding only PET areas above this threshold.
Yeah, I started thinking about it first when I read in your thesis that you tried to analyze the MIP images and that you gave up on it because you couldn't classify them as diseased or not, although medical doctors easily can if they see a MIP. So that's why I thought maybe, there's too much differences between MIP images of different patients, such that the network needs more data to figure out should actually be looking at those hotspots, which DMDs know. So
yeah, I'd also say when I did the MIP bit, I didn't have as much data. I'm sure if I went back, you know, maybe I could make the MIP images work to some degree, certainly as a phase 1. So it's like I said, that you can't test everything, right? Yeah.
Sure it is.
Yeah. But yeah, it's possible because if you've got the MIP effectively, I guess, the way you use the MIP would effectively be just using as a PET threshold, I would say, because you're looking for those dots. So I guess it would probably be a similar effect to just using a PET threshold in 3D, perhaps.
Yeah, and then also Julia asked all the good questions, so I have to ask similar ones. So yeah, about the pre-processing, so you discussed the voxel size. I was also wondering about the intensities, like PET images are quantitative, and somewhere you make a note and saying it's a bit disappointing, we couldn't do better than Submax. So I was wondering, does your network actually have access to Submax? Because if you scale it to 0 mean and standard deviation of 1, it loses quantification. But I saw in some cases you always apply the same scaling to all images. So, but it wasn't clear to me, do you do that all the time, or were there cases where you deleted quantification basically?
I didn't delete quantification, yeah. Sorry, I'm going to edit that in the manuscript and kind of make it clearer, yeah. Well, for MRI, I guess you would, but for PET and CT, I would always keep the absolute differences, yeah.
And then related to that, for the CT, so you raise the minimum from -1024 to -1000, and that had a dramatic effect on the performance of the network, which I find very weird. So did you figure out what actually happened there? Or?
Yeah, so there's actually there's one table that has a mistake in. So there's one that has exactly the same. So table 5.1.7 should have they should be 4 and 8 as SUV thresholds. So there are tables where you actually have very different results with exactly the same parameter settings. So that's one point, but there's still your point with 1024 and 1000 still stands. And this is to do with the CNNs and the instability of retraining CNNs. So what I found, and this is in the couple of chapters later I investigated, was the fact that when you retrain CNNs, they don't necessarily give the same answers. And that's a very worrying for a patient. You don't want to train a CNN and then a patient to be classified as positive or pathological or cancer-free or has cancer. So this is something it's one of those I think it would be really interesting to sort of look at further. And I think reading in the literature, some solutions are you can use an ensemble network, which can kind of iron out those changes, or maybe try and use a Bayesian network. So, rather than having just a prediction, you actually have an uncertainty, because it's no good if your CNN does that. And often if you have a large data set, often this is masked by the actual AUC being the same. So the accuracy or the performance. So you see, you think, the performance is the same, but actually if you look patient by patient, you find it's quite different.
Yeah. So a crude approach would be to train 5 networks and run them all the time and look at the variation. It's a bit cumbersome, of course, but yeah.
Yeah, exactly. Yeah.
And then another thing, when you produce saliency maps, you occluded part of the image, right, to see if it mattered at all for the network, and then checked if the network output was the same or affected. And doing that, you set the image values to 0, if I understood correctly.
Yeah.
And so I was wondering if 0 is an innocent value, because like in a CT, 0 means this is air, or in an MR, this means this is bone but not soft tissue. So is it innocent or?
Yeah, I see your point. And actually, I think it would be a good idea just to test with a couple of values, maybe test with 0.5 and 1 or something. The idea was kind of just to erase the textural information within the occluded region. So I did that, but yeah, I agree that I don't know. I didn't test it, whether it would change it or not. I'm not sure.
Well, it seemed to work because the meaningful results came out, but yeah.
I suspect it would probably do the same thing if you changed it to 1, but it would be worth testing, I think.
Yeah, and if I want to erase part of the network, is there other ways to do it than modifying the image, like maybe 0, some like doing a dropout and dropping out part?
Yeah, I guess you can do dropout. I guess the problem is if you're trying to kind of eliminate a specific section, dropout tries to make the network more generalizable. But
I mean the same trick as dropout. I would just try to turn off part of the network in the first layer and see what effect that has on the.
Okay, yeah. So just don't update sort of one filter in a way. Yeah, I haven't thought about it, whether it would give.
I don't know it either.
Yeah, I haven't seen it used like that, but.
And then another overlap with Julia is this transfer learning versus mixed training. So my guess would be that if you could do what you want, mixed training is probably slightly better. Would you agree with that? Because I guess with transfer learning, if you train too hard, you could forget what you first learned. And
yeah, that's kind of also it's just nicer if you have a model that is trained on mixed data. It's much easier because then you can just use the same model for any data. Whereas if you've used transfer learning, if you've then optimized it to data from one place, it's kind of annoying. But the disadvantage is if you need to share the data, which you sometimes can't.
Well, exactly. Yeah, with GDPR rules, it make it very difficult to do that.
Yeah.
And so it would be very nice to have a way to train a network with data from multiple sites, moving out the network, but not the data.
So actually people do federated learning. So that's where you train a bit from one site and then you send the model to another site and then they train a bit on there. Then they might send it to a third site and they cycle around and you train the model a bit at each site. And then I think as it converges, you probably slow down the training rate or something. And the idea is you try and make a mixed one rather than kind of explicitly transfer learning to specify for one center. You can try and do that. And that's got quite good results, actually. And then you're just having to share the model and nothing else.
So there is no easy way to, well, that's like ordered subsets, right? You train it everywhere, but on subsets of data.
Yes, yeah. So yeah, you've got to.
Yeah, but you're not aware of a way that we can train a network here, and then I can send it to Julia, and she trains it some more, and preventing that it forgets what it learned here without having to share the data with Julia. Because if I do that, we have to sign contracts, and it will take several months.
Well, I think that's the fun. If you're doing the federated learning, the idea is you send it back and forth. So you're just sending the model back
that's cumbersome too, right? And
it is, I guess it is cumbersome. But at least once the model's trained, it is then good at data from both centers. And I've also seen studies that say if a model is trained on data from several centers, it's way more likely to also be better at data from like a New York center. It's more generalizable.
Yeah. All right. Yeah, and then just a final question. So at somewhere you say combat works nicely and it is a lot easier than transfer learning. But I agree, combat is very nice, but I'm not sure why transfer learning is so difficult. If I send you a network and all you have to do is train it on your data, the alternative is to apply combat to your data, right? So is it really simpler?
I guess it's the optimization of transfer learning, which can be cumbersome. I found, that like testing the different amounts of layers, you've got to freeze, testing the learning rates. There's quite a lot more. I mean, it's not the end of the world, but it's just, and also it's kind of methodologically a bit more complicated. So it's almost like an extra degree of complexity to your model that if you're then trying to interpret or explain, makes it a bit more difficult, I guess.
I agree, but I thought that if you send me your network and I have to do transfer learning, I just do what you did. You optimized the learning rate and everything. Do I have to re-optimize it, or can I just continue where you left off?
You might have to re-optimize it or freeze different amounts of layers, and then it may depend. So if I've done transfer learning on data from one scanner, say if your scanner is more different to mine, maybe you need more layers unfrozen, something like that.
Yeah. Okay. Thank you very much, and congratulations again.
Thanks.
Okay, thank you, Johan. And it's a pleasure to continue. So I give the floor to myself as a chair. And I also have prepared a few questions, and also specifically one that I'm trying to deal with. So I hope actually that you disagree with me and that I learned something. And it's about the value of testing, and especially internal versus external testing. So the challenge you sometimes face is that you have a single small data set, say up to 400 cases, which is kind of typical in PET. We call that a large data set. And then you can do two options. You can do just a repeated cross-validation to train a model and assess, say, its robustness on the data itself. And then sometimes the challenge is that the reviewers say, okay, but that's not valid. If you don't have an external data set, just use an hold out internal test. So you take hopefully stratified 20% of your cases separate, and then you redo exactly the same on the 80% that you're left. You do a repeated cross-validation and training and so on. So you have a newly defined model. And then once you applied it on the hold out test dataset. And my argument is that, first of all, that is also just a single point estimate. So you get one value. If you have a lucky draw, keeping this hold out set, you get a very good performance. And if you have an unlucky draw, even if you do it stratified, you get a worse performance. And in some sense, it's not different than a single fault out of your maybe repeated cross-validations. So do you think actually it's meaningful to make use of hold-out test sets?
Yes, I think so, because if you use cross-validation, the more that you use your cross-validation to optimize a model, even you are effectively using your training data in your validation in some way using the cross-validation. So the more, I think, the more parameters you have to optimize during your, because the whole thing, you use your validation data to optimize your model. And with, particularly with deep learning models, there's a lot of stuff to optimize. So you can find that you're going to kind of overfit your models. And even using validation data, I've seen studies that have shown, even using like leave one out cross-validation, you find that you do actually overestimate your performance versus using an external test set or even an internal test set. I guess your point about you might be unlucky or lucky with your test sets, that's completely true. I guess ideally you just want as big a test set as possible, right? And this is just always comes back to the problem of the amount of data you've got. But yeah, I obviously cross-validation is just has to be done at some point, but I think it does slightly overestimate your performance versus if you then did it on a different test set.
Yeah, yeah. Because I think also the practical downside is if you make use of an holdout internal test set, that the sample size that you are left for doing the training and the cross-validation also becomes smaller. And especially if you have quite imbalanced data sets, sometimes the minority class becomes then even smaller and smaller by this step. I do see your point. There's a chance of, say, some data leakage or overfitting, which of course you avoid if you keep fully this 20% stratified internal data separate. Yeah, although I tried with some simulations, and I could not really identify a real benefit, because if you have only 400 cases, reducing the sample size also causes some challenges. That comes back to my second questions. What are the requirements, in your opinion, for a test data set? If I have, just to give your opinion, if I have a test data set that is very similar to the data I used for training, then it may say something about the model, but maybe something less about generalizability. Or should I use a test data set which is maybe the same in terms of diseases and prevalences, of course, but is, say, dissimilar in, say, image quality? Or what would you recommend? And how many test sets should we have? Because one test set is just, you can be lucky or you can be unlucky. Should we have 10 external test data sets instead of only 1 or 2? Reviewers are happy with 1, but I would argue, 1, it's just a lucky or unlucky draw. So maybe you can say, philosophize a bit about what do we need in terms of what kind of external test data sets do we need, and what are the requirements in terms of sample sizes, similarity or dissimilarity compared to your training data?
Big question. So I think I would say, obviously, I think having the more test sets, the better, and the more data in your test set, the better, obviously. And then I think if you've got a very small data set, I guess you've got to make a decision based on, basically you need to be able to build a model that gives you an accuracy. You need to make that model work with your training data. So if you can't make it work with your training data, maybe you need to use cross-validation. I don't know. In terms of using a test set, I think it's nice to have one from the same center and maybe one from a different center. I know that journals are more kind of pushing to have external test sets these days. Because you can have like data from, so normally your internal data set, it's from the same scanner, same protocol, same doctor, same everything. And obviously I think that means your results are going to be a lot better than if you apply it to data from a different hospital, for example. So there's a hospital in the north of Paris where I've got my data from, and it's in quite a poor area. And that means that in general, the patients come to the hospital kind of later, like when their disease is quite far advanced. Whereas there's a hospital in the center of Paris, which is in a really rich area. So the data themselves are very different from the from the two hospitals, and it's very much like a patient problem. So it's not even, it's external to like the scanner and things. So you've also got to think about things like that. And I guess if you built a model from one of these hospitals and trained on data from a different one, you might see a drop in performance. But then, yeah, so I guess in terms of number of test sets, as many as you can get. But it's definitely nice to be able to test from, at least from a different scanner, at least from a different center, and see what happens. And like I showed in my data, I found that directly testing on data from a different scanner, and that was from the same hospital, gave quite poor results. So it showed that I did need to adapt the model.
I think maybe it also relates to the claim that you make. If you want to prove that you have a good model, but it is only good, and if you state that in your claim, it's only good if the image quality meets certain criteria, then of course the restriction of the model is that the model is good, but it may only work on this and this scanner, or this and this kind of spatial resolution or noise level, or a combination of resolution and noise levels. And if your claim is that your model, it can be generalized very easily in terms of requirements for image quality, then I think that is something you have to prove, and then you have to use images with a dissimilar image quality in terms of noise and resolution, for example. I think it's okay to have external data sets that are similar, but I think you should then be clear in your claim that you did not prove that the model works for maybe images collected 10 years ago, which may have a lower resolution.
Yeah, and I guess it's how useful or how necessary it is, because yeah, if it only literally works on data from your scanner, then it's not as useful. Whereas if it works on a wide range, of course, then it's more useful. Maybe it doesn't work on everything, but then yeah, I guess the more you can demonstrate, the more useful it is practically.
Yeah, no, I fully agree. We are not so good in harmonization despite several efforts. So the more robust the model is in terms of our behavior and our scanning procedures, the better. A slightly different question, but also related. So you mentioned also for radiomics about the feature selection, and you indicated the first stage, if I recall it, is to do a univariate selection with either the outcome or your classification, and then subsequently a redundancy analysis based on correlations. So in some sense, this is a supervised approach, because you first try to filter out the image, the features that are not related to your outcome. But there are also fully unsupervised approaches, principal component or vector analysis, for example, but several others, where you do not consider initially at least the outcome or the classification. Which do you have a preference? Because whatever you do, and there are also like maximum redundancy, minimum, or maximum relevance, minimum redundancy, which is kind of outcome and redundancy, but as a one step. If it corresponds to outcome, gets a positive bonus, and if it correlates heavily with a lot of other features, it gets a malus or a penalty. It's kind of a joint selection. But all those approaches result at the end in differently selected features, often, sometimes a bit of overlap. Should we use multiple feature selection methods? Do you have a preference for a certain method, just in general?
Yeah, so this is something I kind of looked into when, before I sort of chose a feature selection method. And again, there are lots of studies that kind of compare them. I wouldn't say unfortunately, there's no, doesn't seem to be a conclusion in terms of which one is better. I guess, again, it probably depends. And particularly in small data sets, the feature selection is absolutely key, because it's very hard to effectively do feature selection when you've got more features, way more features than you've got data. And I think some of the work that I've done, the uncertainties that are like small data sets, is probably a lot of it due to the feature selection. Looking at the features, I found that, like you say, different features got selected completely depending on, say, a different cross-validation, which is obviously basically what you don't want to happen with feature selection. So the method I chose was, I found it seemed to be quite robust, and other studies said it was reasonably robust, and it's quite easy to implement and quite fast. But I haven't done a study on like comparing systematically the different ones, whether it would be worth, say, if you're doing a study, whether it's worth almost doing, almost having an ensemble and doing different feature selections, but then almost that adds another variable that you've got. So I don't know if it's worth having like lots of different feature selection methods and then trying to combine them somehow, whether that's actually going to give you any advantage or it's just making things even more complicated without actually helping. I'm not sure.
Yeah. Thank you. Looking at the time, one final question, which I actually was intrigued also by the presentation, where you compared, say, a more accurate segmentation with the cube segmentation. That's quite interesting. It feels a bit, say, contra-intuitive, that a simple cube, and because it still feels contra-intuitive. Was there any relation between, say, the optimal cube size and the underlying tumor sizes? So was the average tumor size close to the most optimal cube size, or was there no relation at all? Was it related to, for example, if you do a co-occurrence or run length, maybe the settings of those matrices that you choose a certain distance or only within a certain distance, and that happened to coincide with the cube size. So, and then it's kind of maybe natural that you still find reasonable correlations between the good segmentation and the cube-based segmentation. Do you have an idea of what might explain this?
So I think it would be interesting to see how I haven't looked at how the accuracy varies by tumor size. For instance, for the breast data set, actually the average tumor size was about 35 millimeters, whereas the optimum cube size was about 14 millimeters. So actually the cube size was smaller than the the tumor size was much bigger than the optimal cube size. Now, I think probably it depends on the problem. So that was PET based. And I can imagine it maybe because a lot of it might be effectively to do with kind of SUV max being in the center of the tumor, and therefore a lot of the useful information being in the center. Whereas for the lunar data set, the cube size was actually, it's kind of related to Julia's question about does the size of the node on the lunar data set affect the accuracy? But most in the lunar data set, the cube size was big enough so that most of the nodes were within the cube. Like I said, I think it probably depends on the exact task that you're doing, because say if it's a big tumor in the lung, let's say, maybe you need bigger cubes because you actually want to make sure you kind of contain all the information. And maybe it depends where it is. But kind of my theory was that if you've got, to a certain degree, if you've got a tumor there and then you're kind of expanding, as long as you've got the key information within it, it's that my results, what I kind of draw from them is that the radiomic features are powerful enough to extract the kind of useful information, even though there's kind of maybe more information around the outside.
Mm-hmm. Yeah, well, I like the results. I'm not convinced that I will work with cubes, but I think what we have seen also in other studies, that if you have like a classification or a prediction task, that it actually does not matter so much which kind of contouring method you use, whether it's an SUV or a percentage-wise. So the eventual performance of the radiomics machine learning model seems to be quite similar. Which is kind of related that if you really use a kind of very different non-intuitive volume of interest, in this case a cube, that you still find a good performance. So in that sense, you took a little bit more extreme example. So that's kind of reassuring that if you do more plausible contours, that it's actually for maybe a lot of PET questions, a prediction of survival or a classification. We don't have to search for the best segmentation method forever, which is sometimes maybe more inspired by people working in the radiation oncology, where it is important because there you irradiate with the beam, but maybe for a lot of, say, diagnostic or prognostic questions, maybe indeed we can get away with more pragmatic approaches and not do the quest to find the ultimate best contouring method, although I think it should not be a bad contouring method. That's kind of my pick on it. I hope you agree. And then
yeah, well, that's actually where my question came from, because okay. I was wondering how, like, this kind of drive to get a high dice score, and I wonder how much that actually matters for classification. Basically, that was my original question. Yeah.
No, very nice. So yeah, thanks for your answers. I'm quite happy to give the floor to the critics to continue the opposition.
Okay, thanks.
Thank you.
So thank you, David, for your presentation, and more generally, I think this amazing job. So I have a few questions for you. Maybe there will be some technical question, maybe. So if it's not clear, do not hesitate to ask me some precision. So first, I think one big issue is the lack of data you have, so few subjects. And I think then the issue you face is to do some overfitting when you train the model. So you choose some models in your thesis, so the ResNet, the Inception, and so on. So when you have overfitting, it's linked with the number of parameters you want to estimate, and you didn't choose the architecture with the fewer parameters. And I was wondering why. For instance, DanceNet, it's really a compact architecture. It tries to compare this regarding the number of parameters to be estimated. So that's my first question.
Okay, so yeah, I guess, so for instance, for the mediastinal on the second phase where I used a ResNet, I did actually use, I tried using some custom-made models. So I tried quite a few with kind of, with fewer parameters, more parameters. But basically I found that the ResNet model gave a good performance. And actually I found that it wasn't really overfitting on the kind of phase 2. I didn't use a DenseNet, and I would actually, it would be interesting to see what performance it gave. But yeah, again, kind of empirically, it worked, I guess, with enough kind of augmentation and stopping the training at a certain point. So I think if I continue the training, it would have overfit.
I mean, it's the same question, but some details. So you use 2D data as an input of your network. Okay, so when you use 2D networks, you have fewer parameters again. So I think it's a good choice in your case. But do you have a feeling when we can use 3D input data and so 3D CNN? How many subjects do we need to use 3D data directly as an input of the network? And do you think it's interesting?
Yeah, so I guess one thing when you're using 3D as well is, say, for instance, 2D, maybe you'll use whole slices. Whereas obviously 3D, if you try to use the whole body, well, one, the data is just huge, so you might not even be able to fit it in your graphics card. Or, but I've seen quite a few studies that, for instance, they use kind of three slices next to each other. I don't have an exact answer for kind of when, but yeah, obviously, as you had, there's two things, because there's a limit on kind of overfitting because of the size of the model, but there's also just having that size of data in terms of actually like fitting it into the model itself. I would say from studies I've seen, when you have sufficient data, 3D models seem to outperform 2D models, which I think makes sense, because for most tasks it helps to have the kind of the 3D kind of link between the data. But I didn't actually try it, interestingly, for the UNet. I didn't try using 3D data. Whether I'd used kind of three adjacent slices and input that, whether that would have improved the performance, I'm not sure. It would be kind of maybe something worth trying, actually.
So maybe I have also a question on the preprocessing, and more specifically, when you use a 3D patch, so you just split your data with small 3D cubes of different sizes. So you use different sizes. I don't remember, it's 30, 50, and 70 millimeter, but you didn't retrain the network because it's easier. So that's true. but I think it's a bit dangerous because when you resample the data to the same size, you're changing the texture. So I think the first layer of the network will not behave the same way. Do you think it's a limitation maybe of your test here, or maybe I didn't understand well the
Yeah, so I did retrain the network. I retrained the network, but I just resampled so rather than, I had the same network structure. So rather than, having basically every time I trained it with 30 or 50 or 70 millimeter cubes, I resampled the cube size and retrained the network rather than training a different network with kind of a different size input. So my logic was that if I changed the input size, I would then have to completely optimize the network because it would have a completely different amount of parameters and different kind of filter sizes and things. So that was the reason. But I think that was kind of early in when I was trying kind of approaches, and in the end I discounted that approach because I found it didn't give accurate enough results anyway. Does that answer your question?
Yeah, sure. Yes. So maybe just a last question. So it's when you try to extract features with CNN, and then you try to compare that with radio-mix features. So I don't know. I think about representation learning here, and I was wondering why you were not using autoencoder. Did you try that, or is it a perspective of your work?
Okay, so you mean using a CNN and then effectively extracting features at the kind of the representative level?
So the autoencoder is basically when you have an input and you try to reconstruct the same as an output. Yeah. You can use a UNet if you want, and then when you are at the bottom of the architecture, latent space, and you have your feature space here, but there is no classification task or something like that. You just use an autoencoder. It's not supervised. And then you try to maybe do a SVM in this latent space. Did you try that, or?
I didn't try that. I guess because because I actually had a classification task to hand, I suppose. So because it was when I was comparing the radiomic and the deep features, for instance, for the brain data set, I had the task. So I thought it's probably easier. I don't know. I haven't tried with an autoencoder, but to me, the obvious solution was to actually just use the labels to train the network and then just extract the features from the final layer. But yeah, I don't know. Maybe an autoencoder, because I guess the thing with the autoencoder is you get less task-specific features, right? So the whole thing is that ideally they're not kind of specific to each task that you're doing.
Yeah, sure. It might be less specific, but maybe it's something interesting to test in the future. And also one really interesting thing, it's you do not need some segmentation. It's self-supervised, so unsupervised. I will say so. So it's quite easy to use. So maybe it can be interesting to try such a technique in the future. So thank you for all your answer, David, and again congratulations.
Thanks very much.
Thank you very much, Antoine. And we continue with the thesis supervisor, who's Irene Buffat, and she can or cannot ask some questions to you as well. So Irene, the floor is yours.
Thank you, Ronald. Thanks a lot. First, I would like to thank you all for having accepted to evaluate David's work, and also for the interesting discussion and questions that you ask. I won't ask any question to David today, but I would rather like to give some elements of context, as his thesis was somehow quite full of unexpected events. So it was not a smooth thesis. So first, David was the first in the lab to work on deep learning. So he brought that knowledge in the lab. We had no experience with deep learning. And so that was, not easy for him, because he was really a pioneer in our lab to work on that topic. And when he came, he had no knowledge at all on medical imaging. So he had to learn medical imaging and apply his knowledge in machine learning to that new field, or at least that field that was new to him. Second, his thesis was part of an innovative training network led by Thomas Bayer from the University of Vienna. And the topic of that ITN project is actually about exploiting at best multimodality imaging with an emphasis on PET-MR. So David was initially supposed to work on PET-MR data, but we soon realized that we would never had enough PET-MR data for doing deep learning. So he had to switch gears and work mostly on PET-CT data and also on some public data sets, as you could see from his manuscript. Third, being part of an ITN is actually great, I think, but it also involves a lot of side tasks in addition to doing one's own research project, and it takes a lot of time, actually. And in particular, one very interesting aspect of these ITN lies in the secondment. So going to a different lab to work with different colleagues on some specific subject. And David was really unlucky with that part because the first secondment was not very successful because the person who was supposed to welcome him was not here, actually. And the other secondments were cancelled because of COVID-19. So he was really unlucky on that. And obviously, COVID-19 had an impact on the organization of his work and complicated the retrieving of patient data from the hospital. So again, he had to find other data set to go on working in the lockdown period, actually. And even worse for David, COVID ruined one of the fun parts of the thesis, which is going abroad to attend conferences in very nice places and also, of course, interact with colleagues. And the only conference that David could go to was a IEEE conference in Manchester. So for a UK resident, you can understand that it was not a very exotic destination. And last, the lab moved in the middle of the thesis of David, so he had to move as well. But despite all these unexpected events, I think David did very well. And it was really a great pleasure to work with him. And he's actually more interested in, understanding how deep learning and radiomics work rather than just building models empirically. And I share that greater interest in understanding how these things work instead of just designing models. So we get along quite well on that. And also David had plenty of good questions, original ideas, and he was very good at designing the proper experiments to test an assumption, which is exactly what we expect from a researcher. So this was very nice. And he's also very open-minded, so we could discuss, weird ideas, and it was really a great pleasure to work with him. So David, I won't ask you any question. I asked you plenty during the past years. So I would like just to thank you for all the work you did, because you made us improve a lot in that complicated field of deep learning and in our understanding of the potential of these methods, but also of their limitations and on what we can do with them in that medical imaging field. So just thank you, and I wish you the best for the future, and I'm confident that you will do very well. Thanks a lot.
Thanks very much, everyone. Thanks for the virtual clap. And yeah, thanks for all attending the defense and reading the manuscript. I know it's quite long, and yeah, I'll keep in touch in the future, I guess.
Okay, thank you. I think it's now time for us to retreat in the deliberation room, and then we will get back to you soon. So let's see.
Okay, so I guess Christophe will create the breakout room for us, and we will be back in a few minutes.
The room is still there, I think. No,
Should we just press leave?
no, I have a button that says breakout rooms, so I guess if I click there.
I don't see that button actually.
Between record and reactions for me.
Ah, yeah. There's
At the bottom, yeah.
the bottom where it pops up.
Ah, yeah.
Join breakout room.
Yeah,
If
so
press
maybe
on
you
that-
can just rejoin the breakout room. Actually, that might work.
Okay, so let's try that. Yeah.
Okay, see you in a bit. Salut.
Salut, on est tout seul.
Oui, c'est fait.
Ouais, c'est fait, c'est bien.
Merci.
Bravo. On va te féliciter ensuite, mais ça devrait bien se passer.
Ouais.
Surtout qu'elle a oublié, Irène a oublié tous tes problèmes techniques. Les cartes vidéo, les serveurs.
Ils sont toujours là dans
Eh
le
oui.
bureau.
C'est sous-jacent. C'est des erreurs permanentes.
Ouais, pour la prochaine étudiant, peut-être.
Alors je vois que la communauté s'impatiente. Fanny veut même une petite chanson.
Absolument pas.
Absolument pas. Ou on va la connecter, elle va chanter sa chanson.
Okay, thank you very much. We are all back in the public area of the Zoom, and yeah, it is my pleasure, David, to very shortly summarize what we've been discussing about in our deliberation. I think there was, oh, sorry, Antoine is John, yeah. There was consensus on that you gave a very nice and excellent presentation and overview, so that was very clear, and we also felt that it actually added additional information and also insights to us on top of what you have written down in the thesis, so that was very clear. And I think there's also consensus that the defense itself went very well, so you were able to address and to give your view on all the questions we raised. So I think it was really like a discussion rather than a question and answer session. So very well done. My compliments for that. And also we learned that you were one of the first students working on AI and in the lab. So you faced all the challenges of a first PhD on new projects, which are, it's always better to be the second one on the project, but you were the first one, which means that you have to take care of setting things up and also working within the ITN network, which I think was very interesting, but it was maybe also sometimes a challenge. So we all acknowledge that some of us are actually part of the same ITN network. So we have also seen this from nearby. So excellent job. So I think with pleasure and with consensus of the committee, I'm happy to grant you the title of doctor at the University of Paris-Saclay in the medical imaging and medical physics specialty. So congratulations. And also, personally, I would like to congratulate you with your obtained degree.
Woo! Thanks so much. Thanks. I got my champagne here ready.
Is it a French one?
It is. It's Richard de Champagne Bru. I brought it over from Paris. Don't worry.
Okay, but it's not from Orange. Orange. Well, our king is still, I think, Duke of Orange, something like that. Okay, I don't know if, yeah, I already congratulate you. I will give the floor to others if they want to say a few things, and then after that, I can close the session.
I'd just like to say a big thanks to the lab and my colleagues again, and just to Irene for being a great supervisor. Really kind of, yeah, our meetings were always really useful and helpful, and I felt the kind of always came away from the discussions kind of feeling more directed, and I think kind of having more ideas. And yeah, I think I sent you quite a lot of things quite late in the day sometimes, and before conferences or meetings or even the thesis defense maybe. So thanks for always giving me feedback quickly enough.
Well, thank you, David. It was a real pleasure to work with you. It was really fun. So thanks a lot. And you, all what you brought in the lab will be very useful for the future. And it was tough for you because you were the first one to struggle with GPUs and so on. And no, it was really great. Thanks a lot. Excellent job. Thanks.
Thanks.
Well, big congratulations from me as well. It was great also to have you part of the ITN team. It was really nice meeting everyone here, actually. But it's nice to see the PhDs now popping out like champagne, of course. So that's great.
So thank you all. I would like to thank Ronald, who was for his first experience as a chair of a French PhD defense. You did very well. Thank you, Ronald. It was very helpful. Thanks a lot. And thank you, Julia and Johan and Antoine, for the time spent at reading the manuscript, which was dense and very well written, in my opinion, but still dense with a lot of results. So I know the time it takes to go through all that. So thanks a lot for the time spent on that. And again, thanks to David. And David, we are waiting for you being back in Paris, because we would like to celebrate, in person and not remotely.
Yeah, I'll be back once I've got a job and actually start earning some money.
Okay. You want to address some words, Johan?
Well,
you were unmuted, so maybe I was guessing.
Yeah, happy to congratulate David again, and also Irene, because the promoter has usually a non-negligible impact on the whole thing. So congratulations to both of you. Well
Thank
done.
you, Johan. Thanks a lot.
Yes, so David, again, amazing job, and really congratulations for that, because it was, I think, not so easy every day, especially at the beginning, because you were alone to face all these challenges. So yeah, congratulations, David.
Thanks.
Okay, thank you. Then yeah, I think we can close the session. Hopefully you can celebrate a little bit in the smaller inner circle. I understood from Irene you can now receive up to 6 people.
I'm actually quarantined in the UK and can't leave my house.
Oh, that's bad. Yeah.
So okay. I can go in the garden to celebrate, and that's about it.
Okay. Okay. Well, thank you all, and yeah, enjoy the rest of the day. And hereby I close the ceremony and the session.
Thank you, Ronald.
Thanks very much, everyone.
And hopefully see you soon, in person.
Yeah.
Bye-bye.
Likewise. Bye-bye.
Thank you.
Bye.
Et merci beaucoup, Christophe.
Yeah. Merci, Christophe, pour le support technique. Merci beaucoup.
Pas de souci. Au revoir.